Hello everyone, and welcome again to Subject Math. Today we'll be learning about Newton's laws of motion. Newton's first law of motion states that heavy objects at rest or in a state of constant motion will continue at that position unless acted upon by an external force. Now, what that implies is that every object will remain static except an external force acts on it. I'm going to use my board here as an example. This board will remain at this position except I apply a force. Either I pull it or I push it. You can see that it's making that sound because a force is applied. Now, inertia also is the property of the body to remain at rest. Inertia is the property of the body to remain at rest. Inertia is the property of a body to remain at rest. So the property of the body to be static is called inertia. Now I'm going to use a log of wood and also this paper. If I place this log of wood on the table and I apply little force, you will agree with me that the force may not be enough. If I just apply very little force, it may not be enough to move this log of wood. Meanwhile, this paper, I could just blow. This is the paper. Let's say the paper is on the table, and I blow it. Just little force, paper will fly away. Now, if I do the same thing to this log of wood, I'm applying force in form of air. You can see that the pressure, the force is not enough to even move this log of wood. Why is that? That's because the weight of this wood is higher than that of the paper. So what does that imply? That means the more massive an object is, the more inertia it is. So, mass is directly proportional to inertia. That means when an object is heavy, it will have more inertia. Like the example I cited. The piece of paper, we have a lesser inertia than the log of wood. That's because the paper is lighter. So I hope that's explanatory. Now, another concept I would like us to look quickly into is there's something we call mass. You know, we said mass is the concentration of matter in a body, in an object. But another concept is inertial mass. Inertial mass. We said the tendency of the body to remain at rest is inertia. So inertial mass, what is that thing that will help the body to remain at that rest position? That means the more massive the object, the more inertia. So the inertial mass is the body's resistance. Do you understand? The body's resistance to motion. That is what the inertial mass is. The body's or an object's resistance to motion. The magnitude. So the resistance of a body of a body to motion is called as the magnitude of resistance. The magnitude of the resistance of the body to motion is called inertial mass. So, I believe that is very clear. Quickly, I would like to clarify a concept here. For Newton's law of motion is not only limited to bodies at rest. It's also applicable to a body experiencing constant speed. Probably you have a car, and then this car is traveling at a constant speed. Constant speed, let's say 15 meters per second. Let's say this car is traveling at 15 meters per second. At 2 seconds, the speed was 15 meters per second. At 4 seconds, the speed was still 15 meters per second. At 10 seconds, the speed still remains 15 meters per second. For such body, Newton's first law of motion is applicable. So such body will continue in this state of constant speed unless the force is applied. The force could be in form of acceleration or deceleration. Of course, when a deceleration is applied, that means the body will be brought to rest, and as such, the velocity will change. Or when it's accelerating, the same thing is applicable. So for a body either at rest or a body at a state of constant motion, like what I just explained now, it will remain at that stage to maintain that position unless we have external forces acting on such body. Newton's second law of motion. The law states that the rate of change of momentum is directly proportional to the force applied. So for a body at rest to move or to change its state, the magnitude is directly proportional to the force applied. That means the greater the force applied to a static body, the higher the distance moved by that body, or the higher the displacement of that body. So, if you are to represent this mathematically, it states that force is directly proportional to change in momentum. So I have this change in momentum, that's mv minus u over t. But you recall that acceleration is final minus initial velocity over time. So if we substitute this into this equation, I call it equation start. So we are going to have f is directly proportional to m. The whole of this is my a. So I'll just substitute it. And then I have f equals to remove this constant, k and a. I'm just going to say k is equals to 1, the constant. So I have f equals to m. This acceleration is in meter per second square. This is in kilogram. So the unit is kilogram meter per second square. Or Newton. So force has this unit, either this or in Newton, which equals to capital N. So we are going to be looking at one or two examples using Newton's second equation of motion. The first example here says the truck of mass 3,200 kilograms moving with a velocity of 10 meters per second increases its velocity to 20 meters per second from the mass is 3,200. Now, moving with a velocity of 10 meters per second increases its velocity to 20 meters. So that means the initial velocity, which is v, is 10 meters per second, and it increases to 20. That's the final velocity, v, is 20 meters per second in 5 seconds. So the time here is 5 seconds. So those are our parameters. So the time here is 5 seconds. So now we are asked to calculate the F, the magnitude of the force. The magnitude of the force. Recall F equals to M final minus initial velocity over T. So our F is equals to, the mass is 3,200. The velocity final is 20. The initial is 10 over the time is 5. So I have 3,200 times 10 over 5. 20 minus 10 gave me 10. So this is what I have now. 5m1, 5m2. So 3,200 times 2 is 6,400. You know, we said force is measured in Newton. So I have F equals to 6,400 Newton. Another example here says a moving car of mass 800 kilograms experiences a frictional force of 200 Newton, accelerates at 2 meters per second squared. Calculate the magnitude of the force. That's calculate the size of the total force applied to the car. So we have a mass to be 800 kilograms. Frictional force is equals to 200 Newton. Acceleration equals to 2 meters per second squared. So, what's the force applied on the car? Force on the car is equals to, is given by F equals to MA. So, according to second law, F is equals to, we have our head to be 800, our A, which is acceleration, is 2. So I have 1,600 kilogram meter per second squared, or 1,600 Newton. Like I told you earlier, that's the force applied on the car. But the question says calculate the magnitude of the force applied to the car. So here, this is one of the forces, while we also have frictional force. So the total force applied to that car will be the frictional force plus the normal force applied to move the car. So the magnitude of force applied will be equals to the frictional force plus the force in moving the car. So now we want 800, 1,600 Newton plus 800 Newton. And altogether, that will give me 2,400 Newton. You can see it's very simple, and I believe it's well explanatory enough.
Another concept I'll be talking about now, still under Newton's second law of motion, is collision. When we have two bodies colliding with one another, their collision could either be elastic or inelastic. Elastic or inelastic. Now, for two bodies colliding, their collision is said to be elastic when, after collision, the momentum and kinetic energy are conserved. That means before they collided, before that, their momentum and kinetic energy before collision is equal to the momentum and kinetic energy after collision. So for such collision, we say the collision is a perfectly elastic collision. While for an inelastic collision, when you have two bodies colliding, such that only the momentum is conserved, but the kinetic energy is not conserved. It changes. For inelastic collision, the kinetic energy changes. And usually, the kinetic energy before collision for inelastic collision is usually greater than kinetic energy after collision. Before collision. So, when two bodies come together, collide together, and after colliding, they share a common velocity, then you should know we are talking about inelastic collision. That means their momentum is conserved, but their energy is not. So, we'll be considering some applications of collision. The first one we'll be looking at is the recoil of a gun. We'll be considering Okay, so the first application here is in the recoil of a gun. Now, for the case of a gun, when we pull the trigger and then release, we find out that the momentum of the bullet fired, is equal to that of the gun, but their velocities are different. So, this is the way it works. Here is the momentum. The bullet is fired in this direction. Then there is a recoil velocity acting in the opposite direction. Recoil velocity of the gun. Gun's recoil velocity. Here, this is the bullet velocity acting in this direction. But you must take note that both of them have the same momentum. Now, the kinetic energy of this bullet is greater than that. The kinetic energy and the velocity of the bullet is greater than that of the gun. While the mass of the gun is greater than that of bullet. So kinetic energy of bullets greater than kinetic energy or velocity of the gun. So it's very important that you take note of that. So quickly, here is an example. We're just going to apply that in this example. A gun of mass 2.0 kg. So the mass here is 2.0 kg. That's the mass of the gun. A bullet of mass of bullet is equals to 1.6 times 10 raised to the power minus 2 kg. If the bullet leaves the nozzle of the gun with a velocity of 150 meters per second, that means the velocity of the bullet is equals to 150 meters per second. So the question says, what is the recoil velocity? By recoil velocity, that means recoil velocity of the gun. V, recoil velocity of the gun. That is what we are asked to calculate. Don't forget, I said that the momentum had the same. The momentum is conserved. The momentum of the gun is equal to the momentum of the bullet. So here, mass of the bullet is 1.6 times 10 raised to the power minus 2 times the velocity of the bullet is 150. The mass of the gun, that's 2 times the velocity, we don't know, the required velocity. So this multiplied by this so we have V is equals to 1.6 times 10 raised to the power minus 2 times 150 all over 2. Two here 1, 2 here is 75. So by the time we multiply what we have here, it's going to give us 1.2 meters per second. In what direction? It's going to be due, is it due east or due west or due north or south? Now, that will depend on fire the bullet of mass or the direction in which the bullet was fired. He said east, here they said east. So the velocity, you know I told you that the bullet is acting forward while the gun is acting backward in opposite direction. So if the bullet is acting to the east, then that means the opposite direction of east will be west. So the required velocity will be 1.2 meters per second due west. I hope that is very, very explanatory.
Another application of Newton's second law is jet and rocket propulsion. Now, a rocket has gases in its combustion chambers. So as these gases are released downward at a very high velocity, the rocket is propelled upward with a momentum at this particular speed also. So the momentum, the rocket is propelled upward while the gases are released downward. So both of them are moving with the same magnitude, the same speed, but in different direction. Gas is released downward. The rocket is propelled upward. Okay, so in this case, force is directly proportional or is equal to the mass expelled by the rocket times the velocity. Mass expelled per second by the rocket per second. That's the mass of gas expelled per second by the rocket times the velocity. So we're just going to look at one or two examples. And here we have this. A fuel was consumed at a steady rate of 5, so the mass here is 5 times 10 raised to the power minus 2 kg per second. I said mass expelled per second. Sorry, let me break this down. So that's mass times velocity. And ejected with a speed, we use speed and velocity interchangeably. So here we have the speed to be 4 times 10 raised to the power 3 meters per second. To determine the thrust on the rocket, the thrust is the same thing as the force on the rocket. So we have F equals to mv from here. So we have our m to be 5 times 10 raised to the power minus 2 kg times our v is 4 times 10 raised to the power 3 ms raised to the power minus 1. So by the time we multiply this, we have 4 times pi, this 20, this times this, we give us 10. So that's 200 kilogram meter per second. Or we could just say 200 Newton. So the thrust on the rocket is equal to 200 Newton or 200 kilogram meter per second. The last case we will be considering is that of weight of a body in a lift. Now, for a body in a lift, two forces are acting on such body. You have the weight of the body acting downward, and you have the reaction of the floor acting upward. The reaction force acting upward, and that of the body acting downward, which is weight. So we have this, which is the weight, and you have this acting upward. So those are the two forces. Now we have several cases. For the case 1, if a lift is at rest or is moving downward, then definitely W is equals to F. So that means it's constant. There's no acceleration, then W equals to mg. For case 2, if a lift is ascending upward, the weight of the body will be mg plus ma, addition of these two forces for a lift ascending upward. Now, for the third case, if the lift is decelerating such that the acceleration A is less than g, then we have mg minus ma. For case 4, if the lift is moving upward such that acceleration is greater than g, then we have F equals to ma minus mg. So for the last case now, if the lift falls freely, when the lift falls freely, that means A is equals to 0. likewise my G. So in that case, when A is equals to 0, so W equals to mg minus mg, and that will give us 0. So take note of that, and quickly we'll be examining one or two examples on that. Here we have two examples. The first one says a spring balance which is suspended from the roof of a lift carries a mass of 1 kilogram at its free end. If the lift accelerates upward at, so we have the mass is equals to 1 kg, acceleration is equals to 2.4 meters per second squared. So we are given G to be 10 meters per second squared. So we have to find the reading of the spring balance. So in this case, you will see that the lift accelerates upward. So case 2 is applicable. I told you that there are several cases. So in this case, case 2 is applicable. That's because it's accelerating upward. So for case 2, state that F is equals to mg plus ma for a body accelerating upward. So we have F is equals to, our m is 1 times G 10 plus 1 times 2.5. So we have 10 plus 2.5, and that gives us 12.5 Newton. So the reading of the spring balance from here is 12.5 Newton. I want to believe that this is very, very explanatory. So I'll move over here to the second question, which says a 1000 kilogram elevator is descending with an acceleration of this, and G is this. So we have mass, the mass is 1000 kilogram. Mass is 1000 kilogram. 1000 kilogram. Acceleration is 1 meter per second squared. Our G here is 10 meters per second squared. Don't forget, they said it's descending. So in this case, we are going to use the case 3. Case 3 says that when it is descending and then G is greater than A, so we have mg minus ma. This is case 3. Decelerating. So the tension is the same as the force. So we have M, which is 1000 times G is 10 minus 1000, our A is 1. So I have 10,000 minus 1000, which equals to 9,000 Newton. Therefore, the tension in the suspending cable is 9,000 Newton. I want to believe this is very, very explanatory. 9,000 Newton tension in the suspending cable is 9,000 Newton. So I hope that is very clear and explanatory. Okay, now we move to Newton's third law of motion. Newton's third law of motion states that action and reaction states that, the law states that action and reaction are equal but opposite. Now, one of the examples I'll quickly want us to recall is when I was talking about the gun. When I was also talking about rocket propulsion, that when you shoot, when the rocket is launched, gases are ejected downward, then the rocket is propelled upward. So those are two different reactions. The first was that there was an action of gases being ejected downward. Then the rocket now reacted by propelling upward. And we should note that the same high velocity at which these gases are being ejected is equal to the same momentum at which this rocket moved. So this is moving downward negatively, and this is moving positively, while this is moving negatively. So that explains opposite. Equal in the sense that the velocity here is equal to the momentum here. So there's, for every action there must be an equal and opposite reaction. So here are some exercises I would like us to try out on our own, applying all that we've learned. In case you have questions, you could forward it to subjectmat.com.